Hello everybody and welcome. Today we're going to discuss the solution to the problem unique binary search trees. You're given an integer n which signifies the number of nodes available to you, and you have to create from all of these collection of nodes binary search trees. And you have to create all structurally unique binary search trees. And that's it. Now we want to discuss what BSTs are in the first place. So a node like x will follow this property. The node to the right, z, will be greater than that, and node to the left of it, y, will be less than that. So y, x, and then z. This is sort of the structure we are going to follow. This is important to keep at the back of our mind, and let's go ahead and dive into observations. As I've said in previous videos, it's always a good idea to look at small little cases and then try to build your intuitions from that. So we're going to look at a couple of easy cases. What if n equals to 1? In that case, you have just one node available with you, and so that's the tree itself, trivial. N equals to 2. In this case, you have 1 and 2 nodes available, and so you can have two trees like this. 1 as the root, 2 on the right side of it, and 2 as the root with 1 on the left side of it. Okay, so right away we see either of these two possibilities going in the future. Either we are looking at the sort of this swapping of orientations, or maybe we are looking at changing of root. You know, in this case, we had 1 as the root and then rest maybe we will figure out later. And in this case, we had 2 as the root. At this point, we don't know, so let's go ahead and enumerate harder. Okay, n equals to 3, we see a lot more cases. This makes it easier for us to observe a couple of things. First, that swapping thing is no longer very easy to do. We have to sort of restructure entire trees if we swap. So maybe let's not focus on that right now. We'll keep that as later if we can't figure out a solution. But the root thing looks very interesting because it looks like in this case we have 2 1s, 1 2 and 2 3s as the roots. Maybe this is important and we'll keep this in mind. We also observe a couple of more things. It looks like this case with 2 as the root or with as 3 as the root, we have these structures which look very similar to what we have seen above. This 2 1 or 1 2 kind of structure is exactly what we have seen in n equals to 2. And so this hints at the possibility of a DP. We have repeating sub-problems, so maybe we can use DP. So we've figured out two things. Maybe use DP and iterate over all the possible nodes, considering them as root each time. And then maybe we can recursively figure out how to build the tree. And that's it. That's the core logic of the solution. Now, quick implementation level detail. Let's look at an example to understand it better. Let's say that we are iterating and we are at the current node 4. We'll make 4 as the root, and anything to the left of it becomes the left subtree. Anything to the right of it becomes the right subtree. That's fine. But now let's say that we want to look at right subtree itself. There's one very important thing that happens. See, even when you consider this, say, as the 6th node as the root of this right subtree, you are no longer considering 1, 2, 3, 4, 5, 6, 7, 8. You're only considering 5 to 8. You have sort of restricted the range, because you are only looking at a subtree. This means that keeping in mind the left and right indices are a good idea. And in fact, we'll do exactly just that. We'll recurse keeping both of these in mind, and we'll iterate over all the possible i's in between L and R. And then for each of those, we'll recurse to the left and recurse to the right. Okay, enough said. I think the logic is pretty clear. Now we'll dive into the code of it, which should make things a lot clearer. First, we'll have a recurse function, taking in the input L and R. This recurse is what we're going to initialize the recursion with. The nodes start from 1 to n. So the starting node is going to be 1 and the ending is going to be n, both inclusive, by the way. Usually we keep 0, n minus 1 because we're dealing with indices, but in this case, we have to print these out as the answers. So we'll just keep 1, n. Okay, what's the base case of the recursion? When will we end this recursion? It's pretty trivial if you have seen other recursion questions. If L is greater than R, return right away. But what do we return? Since this is a question of trees and nodes, we're going to return a tree node which is none. So a none node. Pretty simple. Okay. What now? As we said, we want to iterate over all of the indices between L and R. So we'll iterate over that. L and R plus 1. Why R plus 1, by the way? Because of how Python takes range. So we want to consider L to R both inclusive. Okay, we'll have the index in hand. Now what? Well, you have the current index in hand, which means anything to the right and left of it need to be considered. So we'll have lefts as the left subtree, which is going to be recursion of what now? We're going from L, sure. And take this case, for example, we have this as the current I and this is the L and the R. From this point, from L, where are we going? Are we going till I or I minus 1? It's both inclusive. So we're going from L to I minus 1. Similarly, right is going to be recurse from I plus 1 now, skipping over I, and we'll go all the way up till R. Okay. Once we have both of these in hand, what do we want to do? Lefts and rights are, by the way, simply now two trees we want to care about. These are the returns of this recursion. So we want to keep that in mind as well. We'll now iterate over for all left in lefts and for right in rights. Okay. We are iterating over every single possibility now. We're iterating over all of the possible left subtrees and all of the possible right subtrees. And for each of these cases, for each left in lefts and for each right in rights, let's create a particular tree, which is the tree in consideration right now, which is going to be a tree node of I. I is the current node. Tree.left simply becomes left and tree.right simply becomes right. At the end, we also want to return like a giant list of trees at this particular level. So we'll have all, or actually let's just call it trees dot append the current tree. We'll initialize it above here as an empty list. And this is the return of the recursion function. Trees. Okay. Let's do a quick sanity check. Sorry. Recurse is not defined. So we'll just and I think this should fix it. Okay, spelling error, so that's fine. No difference in the outputs, that sounds good. Now we want to discuss the space-time complexities. So in this question, what are we trying to do? We're trying to enumerate and create all of the possible binary search trees. Now, in whatever time we create those trees is the same time as the same space we take to store those trees. You create one tree, you take some time, and you store that tree, you take some space. In this effect, the space and time complexities are going to be the same. But what number exactly? This structure might confuse you a bit, but the answer is actually in the order of Catalan numbers. That goes into an entirely different direction, and the proof of how we actually got to Catalan numbers is a bit complicated. So I'll leave a couple of links in the descriptions for you to explore. Anyways, this was the solution to the problem, unique binary search trees. Thanks for watching.